Welcome back to Bite-Sized Breakthroughs. Today we're diving deep into a fascinating research paper that explores the geometric properties of data representations in deep neural networks. Joining us is Dr. Paige Turner, the lead researcher on this project, and Prof. Wed Spectrum, a leading expert in the field who will offer us some crucial context. Paige, tell us, what are the core questions driving this research?
Thanks for having me, Alex. This paper seeks to understand the role of intrinsic dimensionality, the minimal number of parameters needed to describe a representation, in the success of deep neural networks. We ask, how does this dimensionality change as data is processed through the layers of a network? And how does it relate to the network's ability to generalize or perform well on unseen data?
Intriguing. Prof. Spectrum, can you give us a bit of historical context on this issue? Why is this a crucial question in deep learning?
Absolutely. Deep neural networks are remarkably powerful for tasks like image recognition, but their success seems paradoxical. They have a massive number of parameters, which makes them prone to overfitting, essentially memorizing training data instead of learning generalizable patterns. Yet, they often outperform other models. This raises the question of why they generalize so well. Exploring the geometric properties of data representations, particularly intrinsic dimensionality, is a key approach to understanding this.
So, Paige, how did you approach this problem? What new insights did your research reveal?
We used a novel estimator called 2NN to measure the intrinsic dimensionality ID of representations across different layers of convolutional neural networks, CNNs. We tested these on a range of architectures, including AlexNet, VGG, and ResNet, and found some surprising results.
What were these results, specifically, and what makes the 2NN estimator so unique?
Well, the most striking finding is that the ID of data representations in CNNs doesn't simply increase or decrease monotonically across layers. Instead, it follows a characteristic hunchback shape. The ID initially increases, then reaches a peak or plateau before progressively decreasing towards the output layer. The 2NN estimator is valuable because it can handle curved and complex data manifolds, which is crucial for analyzing the representations learned by deep networks. Traditional methods like PCA, principal component analysis, assume flat subspaces, which is not always the case.
That's fascinating. So this hunchback shape is a consistent pattern across various architectures?
Yes, across the 14 architectures we analyzed, this hunchback shape was generally observed, regardless of the number of layers, size, or optimization algorithms used. This suggests it's a fundamental property of how CNNs process data.
Prof. Spectrum, this is a significant finding. Can you elaborate on its implications? What's the significance of this ID reduction in the final layers?
That's where the link to generalization becomes clear. We found a strong correlation between the ID in the last hidden layer and the network's performance on unseen data. Networks with a lower ID in the final layer generally perform better on the test set. This reinforces the idea that deep networks learn to compress information into low-dimensional manifolds, which allows for better generalization.
Paige, can you delve into the details of this correlation? What kind of numbers were we looking at here?
Sure, we observed a range of ID values in the last hidden layer, from around 12 for ResNet 152 to 25 for AlexNet. Even though the embedding dimensionality, the number of units in the layer, was much larger, the ID was still a strong predictor of the network's performance. We saw a Pearson correlation coefficient of 0.94 between the ID in the last layer and the top 5 score on the test set, meaning there's a strong positive correlation. We even found a near-perfect correlation within specific classes of architectures, like ResNets.
That's pretty convincing evidence. This raises the question of why the ID initially increases, right? What's driving that initial expansion in the early layers?
That's a great question. We believe it's related to the presence of irrelevant features in the input data. Take images as an example. They have gradients of luminance and contrast that might be highly correlated across the dataset, but aren't relevant to object recognition. The early layers seem to be pruning these irrelevant features, essentially whitening the data and making it more suitable for higher-level processing.
That makes a lot of sense. And this is supported by the fact that the ID in the early layers is lower when the input data is already pre-processed to remove these irrelevant features. So it seems like the network is deliberately expanding dimensionality to focus on the truly meaningful features.
Exactly. We confirmed this by adding luminance perturbations to the MNIST dataset. This reduced the ID of the input layer, and we observed that the network trained on this modified dataset exhibited a more pronounced hunchback shape in the ID profile, suggesting that the initial expansion is indeed due to the pruning of irrelevant features.
This brings us to another interesting finding, the fact that data representations lie on curved manifolds, not flat subspaces. How did you confirm that, Paige?
We used PCA to analyze the variance spectra of each layer and compared it to the ID estimated by 2NN. We didn't find a clear gap in the eigenvalue spectrum, indicating that the data manifolds were not linear. Furthermore, the PCID, estimated by PCA, was significantly larger than the ID obtained with 2NN, further supporting the existence of curvature.
For spectrum, could you connect this to the broader field of neural networks? How does this finding about curved manifolds change our understanding of how these networks work?
It's a crucial point. Many theories about the visual system have focused on the gradual flattening of data manifolds as information is processed. This research challenges that view, suggesting that deep networks don't necessarily aim to flatten manifolds. Instead, they achieve linearly separable representations by progressively reducing the ID of data manifolds, potentially through nonlinear transformations. This is a more nuanced understanding of how deep learning achieves its remarkable capabilities.
Paige, we've covered a lot of ground here, but are there any limitations to this research? What further questions are raised by your findings?
Yes, absolutely. The 2NN estimator is still under development, and it has limitations in estimating high IDs with limited sample sizes. We also focused on image classification, so further investigation is needed to see if these patterns hold for other types of data and tasks. Additionally, we observed a non-monotonic behavior of the ID in the last hidden layer during training, suggesting a more complex dynamic than we initially assumed. We need to explore this further to fully understand its implications.
Professor Spectrum, how do you see this research impacting the future of deep learning?
This research is a significant step towards understanding the internal workings of deep networks. It offers a new way to measure and analyze these intricate representations. It has the potential to lead to new training strategies, architectures, and methods for detecting and mitigating overfitting, particularly in the presence of noisy data. It might even inspire new approaches to analyzing complex data in other fields beyond deep learning.
Paige, to wrap things up, what are the main takeaways from this research?
We've discovered that deep neural networks transform data representations in a way that's far more complex than initially thought. The idea of these representations follows a distinct hunchback shape, and this shape is strongly associated with generalization performance. This means networks that are good at generalizing effectively compress information into low-dimensional manifolds. We've also shown that these manifolds are curved, highlighting the crucial role of nonlinear transformations. We've gained valuable insights into how deep networks learn to generalize, and this has exciting implications for future research and applications.
Thank you both for this fascinating discussion. It's clear that this research provides crucial insights into the workings of deep neural networks, paving the way for a deeper understanding and development of these powerful technologies. Join us next time for another bite-sized breakthrough.